So this talk will be on magnetism, Fermi surface reconstructions, and Chern insulators in twisted bilayer graphene. So these phases are not surprising anymore, and few other groups have also reported this. So before starting, I would like to thank my supervisors, Chandni and Arindam. So this theory was done by Youngju, Dongkyu, and Professor Jil Zhang, and we get HBN from Watanabe and Taniguchi. So there are 2 degrees of freedom in graphene, spin and valley. Now, valley is important mainly in the context of topology of the bands. And so this is the foundation of topology in graphene, which was predicted in 2007. So if you open up a gap at the Dirac point around K and K prime valleys, so the bottom of the band exhibits a non-zero Berry curvature, and it is opposite in K and K prime valleys. So now one of the ways to detect the Berry curvature is that you apply an in-plane electric field in the system, and the charge carriers in K and K prime valleys will move to the opposite Hall probes, and you measure Hall resistance, which is valley Hall effect. Now this is of course interesting, but if you take 2 graphene layers and rotate one with respect to another by a magic angle of 1.1 degree or so, the system becomes much more tunable. And if you break certain symmetries like inversion symmetry, you can see magnetic moments at different in K and K prime valleys, but you can tune the valley polarization by changing the carrier density in the system. For example, here you are in the K valley, and just by tuning the carrier density, you can go to K prime valley, which I am going to focus on. So the system becomes more tunable, and as I said, you can break inversion symmetry by aligning with HBN. The anomalous Hall effect was observed at a filling factor of 3, which is odd filling factor in twisted bilayer graphene. So you break inversion symmetry, you polarize the valleys in the system, and you see a large anomalous Hall resistance. And 1 year later, quantized response was also realized. So dielectric engineering is an interesting theme to realize some of the correlated states. I would say that this dielectric engineering stabilizes some of the phases in twisted bilayer graphene. Now, interestingly, if you put a layer of tungsten diselenide on twisted bilayer graphene, you start seeing more interesting phases. So this was the first report on twisted bilayer graphene on WAC2, where they saw superconductivity away from the magic angle. So when we saw this paper, we started working on twisted bilayer graphene on WAC2, because there are some open questions that what is the role of spin orbit coupling, how does it enhance superconductivity, and can you realize topological phases in twisted bilayer graphene in the presence of spin orbit coupling. This is our device. We add a layer of tungsten diselenide on twisted graphene, and this tag is encapsulated by 2-hexagonal boron nitride. And this is the final geometry of the device. We etch it into a Hall bar so that we can measure longitudinal and transverse components simultaneously in the presence of magnetic field. And we can tune the carrier density in the system by applying a top gate and back gate voltage. You can also control the displacement field independently. So this is the color map of resistance as a function of filling factor and displacement field. So you see a central feature which is not changing with the displacement field. So this is the charge neutrality point, and there are 2 peaks which are symmetric about the charge neutrality point. And from the position of these peaks and also the Landau fan diagram, which I am going to show you, we can calculate the twist angle, which turns out to be 1.17 degree. And you also see peaks at around half filling of the bands. Now, so this is at 2 Kelvin. Now I'm going to decrease the temperature to 300 millikelvin and measure Hall resistance in the presence of a small magnetic field. So when we do that, we see a finite Hall response. So here I'm changing the density from left to right. That means we go from low density to high density. and we see Hall resistance something like this. So there are a couple of sign changes which I'm going to focus on later in my talk. And now if we change the direction of density sweep, we see a hysteresis. So is this a signature of ferromagnetism? Now, in order to confirm that, you would like to fix the carrier density inside the hysteresis loop and take a magnetic field sweep back and forth. So when we do that, we see a hysteresis in a magnetic field sweep in Hall resistance, and this appears at or near the half filling of the bands. Then we started taking the density dependence of hysteresis. So I'll start from a filling factor of 1.5, close to 1.5. And so here we are going, this orange trace is basically from left to right, negative to positive magnetic field. And if we change the direction of magnetic field sweep, we don't see any hysteresis. Now I'm going to increase the density. So when we are at 1.82, we see a large hysteresis. So now if we increase the density further, we see a reversal of hysteresis. So here you can see blue trace is on top of orange, and by changing the density, you see a flipping of hysteresis at around 1.87. So now if I plot delta Rxy, which is the difference between up and down sweep, and plot as a function of magnetic field and filling factor, so clearly you can see a sign change at around 1.87. Okay. So the color goes from purple to orange. So now one of the ways to understand this data is that below a critical density, which is 1.86 in our case, you are in the K valley. Now by increasing the density further, you switch to K prime valley. And this leads to a change in valley polarization. So valley polarization reverses, and you see a reversal in hysteresis. So now I'm talking about the ferromagnetism at half filling of the band. So what is so special about half filling? So unlike the odd filling factors which are 1 and 3, so the ground state is degenerate at half filling. So you can have 3 different states. So in the first one, you have equal number of valleys and spins. So the state is spin valley unpolarized. You can also have spin polarized, so in both the valleys, like up or down spin, or you can have spin unpolarized and valley polarized bands. Now, in order to realize ferromagnetism, it is important to create a valley polarization in the system. But in the absence of spin orbit coupling, there is something called inter-valley Hund's coupling, which picks either of these 2 states. So in that case, you don't have any valley polarization in the system, and you don't expect ferromagnetism in the absence of spin orbit coupling. Now, the moment you add some spin orbit coupling in the system, this state is favored. Okay? And because of a finite valley polarization, you can realize magnetism in twisted bilayer graphene near half filling. But this is too simplistic. The band structure changes the moment you add spin orbit coupling in the system, and these theory calculations are by Professor Jiljang and group. So the Chern number changes, but the total Chern number remains the same at the half filling, which you get for regular twisted bilayer graphene also. And you can clearly see valley degeneracy is fully lifted, and near the half filling you get a total Chern number of 2. And also you see a reversal in magnetic moment near the half filling of the band, okay? +2 and -2. So although spin orbit coupling modifies the Chern number, the total Chern number at the half filling remains the same. Yeah. So the Chern number of the valley Chern number of these isolated bands are +-1 and +-3, and this also changes the moment you vary the spin orbit coupling strength, you get a set of Chern numbers. But if you calculate the total Chern number at half filling by adding these numbers, you get it to be 2. Yeah, magnetic sample.
You see a non-zero Rxy, right?
Yeah.
And the and the sign also change. So you're trying to explain the earlier part of the data, right? The experimental data that you showed.
Yeah.
Um,
So sign of delta Rxy changes. Basically, the sign of Rxy also changes for a particular direction of magnetic field sweep. And here you can see that the Chern band goes from blue to red to green. So red is basically K prime, and blue is K. So you go from K prime to K value. So we wanted to understand the ground state little bit more near the half filling of the band. So as I mentioned previously, we see a couple of sign changes in Hall resistance. So now if I convert it to Hall density, I can clearly see two sign changes and minima in between. So this is the zoomed in plot near the half filling. So this is exactly where we see ferromagnetism. Now, before explaining this data, I wanted to tell you a little bit about Fermi surface reconstructions when you have large density of states, which occurs near the half filling of the bands in twisted bilayer graphene. So this is well known that you bring the Fermi energy near the center of this large density of states, and you see a change in type of carriers from electron-like to hole-like or vice versa. This is known as Lipschitz transition. But in the presence of strong Coulomb potential, which is the case for twisted bilayer graphene, you can also see a splitting of the bands. And so because of this splitting, the charge carriers, the type of carriers doesn't change the sign, but it goes up and then comes down to 0 or shows minima and again goes up. So this is known as the reset of carriers, and all these tell you that you have a large density of states near the half filling of the bands. Okay. Now these phase transitions are tunable in magnetic field. So I start from 20 millitesla. I see a couple of sign changes and a minima, a reset like behavior. The moment you increase the magnetic field to 200 millitesla, you don't see these sign changes. Okay. And it shows a peak-like structure, and then it comes down and again goes up. And this continues for higher magnetic field as well. These are also tunable with temperature. So we see these features up to 5 Kelvin or so. At around 8 Kelvin, it's flat. So as I already told you, the density of states is very large near this filling factor, and you have a strong Coulomb potential in the system. So can it be a stoner-like instability which drives to ferromagnetism in these systems? Now this is all about low field. If we increase the magnetic field to 10 Tesla, we see the Landau-Fan diagram, and different features are appearing from different integer fillings, and they are quantized to these numbers. So you can calculate the Chern number from the slope of these features, and we see, these observations are consistent with what people have reported earlier. So now I'll focus on plus minus 2 because this is where we see ferromagnetism. So this is the data at 10 Tesla. So we see a plateau in Rxy, which is quantized to h by 2e square, followed by a minima in Rxx. Similarly, for the whole side, we see a quantization to minus h by 2e square and a minima in Rxx. So now if I calculate the total Chern number by assuming the time reversal symmetry breaking mechanism, so I get a total Chern number of plus minus 2 at the half filling of the band. So we have explored two different regimes of Halley polarization. Near the zero magnetic field, it's stabilized by spin orbit coupling. We see anomalous Hall effect, but it's not quantized. So we believe that this is probably partially Halley polarized instead of fully Halley polarized state. And by increasing the magnetic field, we can polarize the valleys fully, and we realize quantized Chern insulators. So this is the phase diagram. We see anomalous Hall effect near the half filling of the bands, and the low field data is very interesting. There are Fermi surface reconstruction happening at low field, and they sort of smear out if you increase the magnetic field in the system, and we see Chern insulators from different filling factors. So now this is all about the Hall resistance. When we look at the longitudinal resistance of this device, it shows something interesting which we don't understand yet. But before that, I wanted to tell you about 3 types of magnetoresistance which have been reported earlier in magnetic samples, mainly magnetic tunnel devices. So one is this type of behavior. You can also have something like butterfly and antisymmetric magnetoresistance. So all these behavior tell you that you have 2 resistive states, and depending on the direction of magnetic field sweep, you access those 2 states, and the magnetoresistance can be same in positive and negative magnetic field, or it can be different. So if it is same, then it gives you butterfly-like MR, and if it is different, it gives you antisymmetric magnetoresistance. So when we look at our data at around 1.85, we see antisymmetric behavior. The behavior changes by changing the density, and we see all 4 types of behavior in this sample. I mean, don't yet understand what's happening. This is something we'd be happy to discuss about if anyone has any idea. Yeah, so and these features are not random. So if I compare with RXY data, the color plot, so wherever we see a reversal in hysteresis, the MR shows butterfly-like transition, and away from that point, you see antisymmetric MR. Again, I mean, we don't know what's happening. So now I have told a little bit about twisted bilayer graphene in the presence of WSE2, but the Moire system is expanding rapidly, and we recently had an opportunity to write a review article on Moire system. We started with twisted bilayer graphene, and you can take multiple graphene layers and rotate them with respect to each other and start seeing interesting physics and also the flat bands. So yeah, if you are interested, please have a look, and thank you for your attention.
Question.
Reversal of hysteresis. I noticed 2 steps. Is there any understanding on why such a double step transition occurs? It was a bit earlier in the slide.
So initially we thought that these are because of the movement of domain walls, spinning of domain walls.
Like if you go back, it was even more clear there. Yeah, here.
I think this slide.
Yeah, I mean.
So we thought that these are Barkhausen steps, but we don't know because these are coinciding with the RxX data I showed you, step-like structure in MR data. This could be because of the pinning of domain walls and twist angle inhomogeneity also, but it might be something related to the MR we are seeing, the complicated structure, magnetic structure.
So my question is like about the antisymmetric resistance, like hysteresis or these hysteresis. So all these are for the perpendicular magnetic field, right? Mm-hmm. Like but the asymmetric one, I might have missed it. Up to what magnetic field did you sweep? Like
the same range.
So no, these are like more than 500 millitesla, and these are like the right ones are around 200 millitesla.
Right. Yeah. So this is the same range I showed.
No. Yeah.
You're talking
okay.
about the.
Yeah. Okay. So around 150 or something, like.
Yeah.
Okay. Yeah. Okay. So and these are all in perpendicular magnetic field. Okay. Oh, and that was my first question. And the second question is about the Chern insulators that you see at 10 Tesla. Do you have any idea, like, what is the gap, like energy gap? Like, do you have any temperature dependence? Like,
No, we don't have.
Okay. I think it might be a bit difficult to perform temperature depend, like energy gap at for such high magnetic field, like 10 Tesla or something.
Yeah.
Does the anomalous Hall effect disappear at filling factor 2?
Yes.
Thank you.
Any further question? If not, let's thank the speaker.